So yesterday we talked about vapor pressure and all those other things. Hopefully you're all right with that. Today we talked about that. Here we go. We talked about heat of fusion, right? You could explain why this D to E segment is longer than B to C, right? You dang well better be able to. All right, then we got two phase diagrams. Well, I don't know, do we have this definition yet? All right, the boiling point, this is its definition. Boiling point is when the vapor pressure of the liquid matches the atmospheric pressure, which means the desire of the molecule to leave the liquid. We'll measure that at like 1 atm, and that's what the pressure is. So it's going to go from liquid to gas. Then we call that boiling. So vapor pressure matching atmospheric pressure, that is the boiling point. All right, then we have phase diagrams, which I'm going to talk about, but are not tested as of 2021. Okay, so I'll talk about them for a minute, but they're not on the AP test, so I won't have them on my test either. I don't know, they're actually really easy, so it's kind of sad. They removed it because it's considered background knowledge, which I'm sure all of you know about phase diagrams, right? Okay, so just, I don't know, I've never not taught this. Phase diagrams show pressure versus temperature diagrams for a substance. Now, the only reason I'm still keeping up with this is you actually see graphs like these on the ACT once in a while. And you may not have I don't even know what that is. They would ask a question that wouldn't require you to know what it is. They'd say, hey, at what pressure and temperature is CO2 a solid? And then it's any of these. Or is it a liquid? Or is it a gas? I don't know. We'll just talk real quick. It's not on the test though. So this is water. And this line right here, that's the interface between when ice, a solid, and water vapor exists. This doesn't happen to us in our world. Water doesn't sublimate. That's when it goes from a solid to a gas under normal atmospheric conditions. It happens at 0.458 torr, which is almost 0 atm, and under the freezing point. It's a very weird place that would happen. Okay, but carbon dioxide, also known to us as dry ice, is called dry ice because it sublimates at 1 atm and -78 degrees Celsius. So that's normal. We call it dry ice because we never get liquid carbon dioxide. Doesn't make my sandwich mushy or whatever. And that's just because it has different properties, has different intermolecular forces that affect its melting and boiling points and the pressure involved. All right, so this is the solid, this is the liquid, and this is the gas state. Anywhere along this line, we would call that the boiling point. Anywhere along this line, we call that the melting point. Now it changes because it's versus pressure. All right, one unique thing, and they don't have it anymore, is that water has this strange slope. It's the only one really in nature that has a negative slope between the solid and the liquid phase. And that's due to the very complex and ordered structure that water forms as a solid. Same reason ice floats. It's that hydrogen bond and it's lining it up. You don't need to know these anymore, test-wise, but just common sense. If you ever saw something like this, you could sort of reason your way through a lot of questions there. Okay. All right. So I guess I can take these off. There's a few things on the vocab that are about these charts that I can get rid of. And one will be the triple point, which is a really strange thing to even imagine. It's the point at which all three states of matter can exist in equilibrium. And you literally wouldn't be able to tell the difference between the solid, the liquid, and the gas. And I have no idea how that, I just can't imagine that. It'd be like rain and ice and steam all at the same time. So it's kind of weird, but that's the triple point. It happens at specific places, right? So we'd have a triple point right here at 0.48 torr and right above 0 degrees for water. So almost at no pressure and no temperature. Well, not no temperature, but close to the freezing point. No. I can draw an example. You have gas, you have water, and you have ice. And you can't tell them apart. I don't know. Was there pictures of it? Okay, we can look that up in a minute. But the triple point is a very unique condition. Now, it doesn't mean that it's like 30 degrees and it's kind of snowing and kind of raining. That's just weather, okay? Some of them froze up high, some of them stayed liquid. This is a different type of situation. And then I really think that's it. Okay, so on the vocab, let's look at the vocab forever away. And let me tell you what I'll get rid of, because I forgot these aren't even on there until yesterday. Oh, I had them somewhere. I had them right here. Okay, we can get rid of critical pressure. The normal boiling point, you should know as a definition. It doesn't have to be on a chart. Normal boiling point is the boiling point of something at 1 atm. So that's still, you don't need to know this. You don't need to know that. Okay, everything else you should know. I know it's, oh man, it's gonna be a pain to change that, but we'll live. All right, hold on. Like here's a picture that is completely useless in my opinion. Oh, it's a video. Here you go. Okay, there's your triple point. Which it isn't. There's no way this is really the triple point.
Wait, what is happening?
That's a great question. Oh, they did it for cyclohexane. All right, sorry. It could be the triple point. I thought it was a water. I'm like, there's no way someone really did this. Okay, fine. We'll watch the whole thing. Is this what you watched, Tim? Okay, yours was probably more.
Students of the University of
Not-
Manchester in the United Kingdom were trying to identify this liquid when something very unexpected happened.
Oh my god. I was about to say the whole thing's solid. No, it's
This is one of the reasons that I love science. It just does the most unexpected things.
the whole thing just gone.
I have no idea what's going on in this video. Can someone please explain to me how this is somehow boiling and turning into a solid at the same time?
Over 5.5 million views later, it's time to figure out just what this substance is.
What these guys have stumbled across is a very specific pressure and temperature, which scientists refer to as the triple point.
Which is the perfect temperature and pressure at which all three of these solid, liquid, and gas phases can exist. And it takes just a really tiny change in temperature or pressure to flick between one or the other.
So how did our student scientists stumble across the triple point?
It looks like water in that flask, but actually it's something called cyclohexane.
What they're doing here is actually vacuuming out what we call the headspace of the flask, which is the gas that is just above the liquid. Now, because that contains cyclohexane molecules that have evaporated off the liquid layer, by removing that, we're changing what we call the equilibrium.
The system wants to restore this equilibrium, and that means that you get more and more cyclohexane molecules evaporating out of solution. But it takes energy to do this, and as a result, the remaining cyclohexane drops in temperature and freezes.
So the gas at the top of the flask is pumped out, disturbing the balance and making the liquid boil. But boiling needs energy, which is taken from the liquid, making it freeze. Then what happens? Helen?
Now that it's a solid, there's no more boiling and there's hardly any evaporation, and all of the energy is just conserved. But a little bit of heat gets drawn in from the room, which means the solid turns into a liquid, which means the whole cycle starts again. From solid to liquid to boiling to gas back to solid, the cycle goes on and on and on and on.
All right, that was fantastic. It still isn't technically ever showing you the triple point, but that's closest I've ever seen, because it's just not something really observable. I don't know how to explain it, but to observe it, you would ruin it. All right, that is the end of chapter 13. That was fun for me. How about you? Or sorry, 11. All right, chapter 13. I don't know. This is hard for me as a human being right here. Let me just show you something real quick here. No, it's not. That's the problem. Here we go. Yeah. It's because they ripped out every part of my soul here. Because in chemistry, what's my favorite part? The math. They took out like 95% of the math. Oh, the math is easier. Why is this not changing when my arrow changes? That's annoying. All right. What's wrong? Isaac. Oh my. I don't turn the light off anymore. What am I doing? For 10 years, I walked back and turned the light off. Okay, here we go. This is what they feel is important from chapter 13, that you can calculate the number of solute particles, volume, or molarity of solutions. We know how to do all of that. It's been a long time. To find the volume of something, you put it in a beaker that's graduated, or a graduated cylinder, or something like that. All right. To find the number of solute particles, you take the moles and multiply it by a big number that we call Avogadro's number. Does that sound familiar? And then molarity. Ooh, what's molarity? Moles per liter, which we've done a crap ton. Remember that? Okay. So anytime on this thing, which you guys don't ever look at, but if it says EQN, that means the equation that will be given to you is capital M, which means molarity, is equal to N of solute over L solution. What does N mean? Moles. So in chapter 4, and chapter 8, 9, 10, 11, 12, I don't know, you've used moles. We find its molar mass, we given and divide by the molar mass. We've done it 100 times. You all right with that? How do we find the moles in a solution? If I told you had 80 milliliters of a 2 molar solution, all right, moles equals 0.08. That's the volume, right? And we have how many moles? 2. So this is really, or 2 molar, sorry, this is really 2 moles per 1 liter, right? So we just times this by 2, right? Like we've done it a lot. Okay. So, I mean, that one's done. There's, I guess, a lot of words. Solutions, also sometimes called homogeneous mixtures. We learned homogeneous, like we should have. Keely's making a homogeneous mixture right now. Raise your hand up, please. Oh, my perfect timing. She's making a homogeneous mixture. It's a solution of Hawaiian punch. I don't know what it is, but it's something. All right, what do we got? My eyes. Oh, tropical punch. I was close. Hawaii is in the tropics. Sorry, TA. Here was the other pile I never brought to you. And I never brought you a marker, did I? You're a hero. Okay. So they can be in solids, liquids, or gases. We typically refer to them as in liquid. Or gases, we hardly ever talk about a homogeneous mixture of solids. But that would be if I mix sugar and salt. Like we would look at it, just without extreme examination, you'd have no idea which one was the salt or the sugar. What? All right. In addition, the macro, meaning large properties, do not vary throughout the sample. So like that Hawaiian tropical punch, whatever, it's going to pretty much taste the same no matter what, as long as she keeps it mixed, right? All right. In a heterogeneous mixture, the macroscopic properties depend on location in the mixture. So like your trail mix, some of it's going to taste like it has gross raisins in it because it has raisins in it. And some of it's going to taste like M&Ms because that's like all you've got. So trail mix would definitely be heterogeneous, right? Every bite of trail mix should taste slightly different, but never Mountain Dew. It's like always tastes like Mountain Dew. Unless you got a problem. Okay, here we go. That's all review. We had already learned all of that. Okay, next, representations of solutions. Like to an old guy like me, they took math out and now they added drawing. It's like, this is still AP. And the people way older than me, like the pre-1994 ACT or AP, they just probably look at you guys like you're the biggest wusses ever. Because that math was hard. Now, I took chemistry in high school before 1994, but there was no way I was going to take AP. Like, I got a C in normal and was extremely grateful. And I never did get the number of the TA who I was in love with, but whatever. Those are water under the bridge. Yep, it was rough. So instead of math now, everyone looked at the TA. I'm talking about my TA when I was in high school. Okay, not her. Are we clear on that? Okay, that was like 20 people looked at her like she must feel really awkward. I knew what you meant. Okay, what's that? Oh, they're like, so I'm just gonna send it and get Amber's number. Okay, that makes me feel more comfortable. All right, so we're gonna draw now instead of do math. So it says using particulate models of mixtures. Bunch of circles. So a particulate model would be like, it would say, draw a solution of salt water. And so you'd put like a Na plus, that was a stupid way to put it, but whatever, and a Cl minus of salt water. Like, that's like all you do. It's like, what? Give me math or give me death. All right, but no. I don't, that might not be the right quote. That might not be the right. That was something like that. All right. So thank you, Seth. All right. So drawing these are not typically super hard. A lot of times, I guess, oops, it is a little bit trickier. And if you're wondering like, what kind of order is he teaching this? I don't know either. So here we go. It might be something like draw a solution of CaCl2. And then what are they looking here? What's going to be different? All right, you better have one Ca to every what? 2 Cls. What's that? yeah, this is the right stuff. Read the thing. Like, I'm not making it up. Well, don't worry. I'll find a way to make it way harder so you fail. All right. You're welcome.
Actually showing them
Oh, no.
UHSAA? No, I mean the actual stuff from.
AP.
Oh, it's AP. Never mind.
What did you think I was showing?
The whatever from the core.
Chemistry doesn't have a core right now.
He's showing us what disappointing to you. All right.
They took math out of this unit.
You want to explain to people how I get the whole box filter of everything down? I went sat at my desk. I could not figure it out.
Okay, good. All right, represent interactions between components. Ooh, what do they even mean by that drawing? Sort of, don't say bonded. Say they're intermolecular forces. That's what I'm looking for. Okay, so, whoops. So it might be something like this. You have your Cl minus, and then it wants you to show the interaction between it and water. How would you draw that? Just draw water? Nope, false. It's important how you draw water.
You draw the little Mickey Mouses, then you draw the positive and negative side.
Okay, so Cl's a negative. So what part of the Mickey Mouse should touch? The ears. So we'd have H plus O, H plus O, H plus. Now, AP is getting more specific. A lot of times they'll say, show the interaction of 5 sodium chloride atoms dissolved in water or something like that. So you need 5 Cls, 5 NAs, and it might say 20 water molecules or something. Like it might give you specific things. We did this 2 tests ago. Does that sound familiar? Okay, so these should not be super duper hard. We've kind of covered them already. Okay, coming back to what AP thinks is important. All right, this is what blows my mind. Oh, sorry, representation of concentrations of components. So that, once again, you'll just draw more of the thing that's concentrated and less of the things unconcentrated. And they'll give you numbers specifically, I'm sure. Like the CaCl2, you need 2 Cls to 1 Ca, stuff like that. Okay, this colligative properties will not be assessed on the AP exam. Celebrate, because they suck. Ready, go. All right, there we go. Moving on. All right, this calculations of molality, percent by mass, and percent by volume will not be assessed in the AP exam. These are units of concentration. And we've already learned percent by mass. We haven't really talked about it with solutions, but it's just taking the percentage of something, which we do with moles and other areas, just not in solutions. Molality is a measure of the kilograms of solute, the moles of solute per kilogram of solution, and it's a little bit different. It's tricky, right? It's really tricky. Molarity is really, really useful, but the problem with molarity is it is temperature dependent, which honestly, it is not that temperature dependent, but it is. Molality does not change depending on the temperature, so who cares? Abby's rolling her eyes, which means she doesn't think molarity is temperature dependent, right?
Oh, I don't know. I'm just confused because that sentence had temperature dependent a lot and then not temperature.
Okay, molarity is moles divided by volume, right? Volume is temperature dependent, which means that molarity would change as the temperature changes. But in most conditions, it's extremely not significant enough. But when it does really matter, then they'll use molality, which does not depend on the temperature of the substance. But who cares? Not on the test anymore. Okay, moving down. So this was where the most of the math was, the colligative properties and the molality. And then we have this that is usually not even in this chapter. So most of everything we've either done or is taken out. So let's just dive in. I'm going to go through the lecture. I might cover this in a day. I don't know. We're going to test when I feel like it in the next few days on chapter 11. And it's going to be 99.9% qualitative, which means no math. It is lame because math has an answer. The explaining stuff is hard. Okay, here we go. All right, solutions. We've already said this. They are homogeneous mixtures of two or more pure substances. In a solution, the solute is dispersed uniformly throughout the solvent. Chapter 4 is also about solution stoichiometry. So we have already gone over most of this stuff. But here are some examples of solutions like air. We don't really think about it because you think of solution like salt water, but there can be gases. Air is a solution of nitrogen and oxygen mostly, then carbon dioxide and water vapor and other gases as well. Are we all right with that? All right, oxygen and water solution, alcohol and water, salt and water, hydrogen and palladium. What? Well, just trust me, this makes like cells for, no, hydrogen cells. It helps that happen. Mercury and silver, weird, but those are two metals you can pour together at certain temperatures and they'll mix evenly. And then silver and gold. Yeah, it is. It's really messed up, but you can. What?
Why is it messed up?
You can mix liquid silver and mercury, and they will make a homogeneous mixture of silver and mercury atoms.
Mm.
That seems like so legal.
You wouldn't want to do it because anytime you get mercury hot, you're going to get mercury vapors, and those are what kills you. Like everyone's like, oh, mercury is really bad, but it's the mercury vapors that really get you.
So as long as we wear masks, we're set.
You should be fine.
Yeah, man.
Like old people have mercury in their fillings, in their head,
Wait, what?
but that's okay. They're not like pure mercury because that'd be a liquid, but they're alloys for your amalgam. Is that what they're called? No, is that, yeah, amalgam and composite? Any pre-dental majors?
No.
Anyway, there was mercury in them a long time ago. I'm young enough, and I know I'm old to you guys, but there was no mercury in mine, but my grandparents would have mercury in their fillings. Okay.
The more you know.
Here's a definition. The solute is the thing that has the lower concentration. The solvent is the thing that has the higher concentration. That's 100% of the time. So we always usually think that the solute is the solid, the solvent is the liquid. That usually works for like 99% of things. But if I had a cup full of salt and I added a little bit of water, then it would be reversed because the salt would be the high concentration, the reverse. But usually you can get away with that. The solid is the solute, the liquid is the solvent. And in this class, almost 100% of time, the solvent will be water. All right, so in salt water, your salt is your solute, your water is your solvent. Easy enough. Okay, we've already gone over it. Okay. So here's some ways to nerd it up. The intermolecular force between solute and solvent particles must be strong enough to compete with those between solute particles and those between solvent particles. Yep, so this is solubility, which we talked about in chapter 4. What it's saying is, in order for something to dissolve, the particles in the solute have to be less attracted to each other than they are the water molecules or the solvent. If the attraction between them is greater between the solute and the solvent, then the substance dissolves or is solvated. If it is not, then it sticks together. So something that we had, like we said, lead chloride or lead 2 chloride was not soluble, right? And that's because the PbCl2s are holding on to each other tighter than the water could pull them apart. You okay with that? Strong. And then this attraction would be weak. And so it's not very soluble. All right, but like sodium acetate, NaC2H3O2, very soluble, very dissociative. The Na plus is very attracted to the water. Now I would draw the ears away, right, and the head by this. But the acetate, I'd put the ears on and then put that there. Do you know what I'm saying? The O minus and the H plus. And then the, whoops, what am I doing? Yeah, you started it.
I know, I'm so proud of myself.
Where did I lose you?
Never mind. I was just confused when he starts talking.
I can relate. Just kidding. Corman's usually pretty bright. Are we all right with why oxygen and sodium? I almost said nitrogen. That's embarrassing. Why that is the way we would line those water molecules up? Okay. Feel like, I hope we are. Okay. How does a solution form? I bet you've always been wondering that. As a solution forms, the solvent pulls solute particles apart and surrounds or solvates them. Oh, cool. It's like chemistry seminary. We're talking about your solvation. This is a good joke, I thought. I mean, good mix of church and state and humor and chemistry. Okay, everyone's offended. Okay, so the water, you can see right here, it has surrounded the molecule and it has pulled them off. Now the reds are attracted to this molecule. So what do we think that is? We don't know, but it's positive, right?
It's small and
Okay.
positive.
All right, next.
Probably the generic.
Yeah.
So,
So if an ionic salt is soluble in water, it's because the ion dipole interactions are strong enough to overcome the lattice energy of the salt crystal. Ooh, I feel like I've heard of an ion dipole interaction before. Will you tell your partner what an ion dipole interaction is? All right. All right, let's come back real quick and we'll do it. So in this picture right here, let's see how, oh, I gotta, no, I'm not gonna blow it up. In this picture right here, what color is the ion dipole attraction? That's the blue one, right? We know this substance is polar because water's polar, right? So we know we have a slightly positive and a slightly, okay, that was whatever, negative here, right?
What that S means is slightly.
No, it means sigma, but slightly is good enough for me. It's the snakety snake, which means slightly positive or slightly negative. That comes from Bert, not me.
But he says it all weird. Like he doesn't.
Oh, well, Bert's weird, so. Okay, so an attraction between a polar substance and an ion is an ion dipole interaction, okay? Then, when I read lattice energy, someone that's sitting right in front of me said, lattice energy?
I know, I said lattice energy, like, I don't know.
Oh, okay. I thought it was I've never heard of that, but it was oh, I have heard of that before. Lattice energy, you may remember, is the attraction of the Na plus to the Cl minus, right? So if they're gonna break, then ion dipole wins over lattice. If they don't, then lattice structure beat ion dipole. Fair enough? All right, you guys are awesome. What? Okay. This is going to get a little bit tricky, so I'd pay attention the next few minutes. Are we ready? there are energy changes in a solution. This will be the only complicated part of all of chapter 13. All right, so I wouldn't write all this, but simply put, 3 processes affect the energetics of a process.
Wait.
That's really stupid. I didn't type that. Okay, the separation of the solute particles, the separation of solvent particles, and the new interaction between solute and solvent. I don't know. Write what you want after I talk through this. So what we're saying is, how can I put this with my church example here? Okay, so you put a solid into a liquid. The first thing it's going to do, if it's going to dissolve, is going to be attracted to the water molecules. You okay with that? But the next thing that happens, you wouldn't think about it, but the water molecules themselves have to make room to allow that to come into the environment. You with me? If there's no room, then it won't go. And that's why it's harder to dissolve things than things that are already. Because there's not more room. That was really weird.
All of a sudden, like, I could hear there and there.
Yeah, that doesn't happen to you very often, but it happens to me all the time at basketball games. Because I mute the mic on and off constantly. And then I'll be like, 11, and everyone looks at me weird, like, turn your mic on. Shut up. Speaking of, Seth, should I bother playing the song? It has not worked a single time. No one dances. Not a single person.
Wait, what?
I just sit there and look stupid.
My mom's thinking about the music. My mom was gonna come and help.
Okay, that's fine. Seth's mom.
Wait,
Okay,
what's
come to the
happening?
games.
When's the game?
It's tonight, the girls' game.
Okay.
And now half of you are like, oh, it's a girls' game. I'm not going. Well, screw you people.
What's
The
happening?
girls' games this year are pretty entertaining.
If I don't go to the game in general.
If you don't go to both, I'm okay with that. But if you only go to the boys, you annoy me.
What time is it?
Okay, it's at 7.
Oh,
Okay, look at the screen. So here we go. Seth's still writing, so I'm not going to advance, but I'm just going to draw a beaker here. There's an attraction. It goes, the liquid has to move apart to make room for it. Now, so I have a minivan and I have 6 kids. So what's the fight over every time? The middle, because my wife and I get the front. So the middle front. So the kids get in, and nothing makes me more angry than when we're like all 6 going to get in the car and the first 2 people sit in the middle. I want to kill them. I love them, but why do they exist if they're that stupid? If you call the middle row, great, but you can't get in at first, because what happens?
everyone else to get
Yeah,
in.
it takes work to make room to let someone get in, right? So this is the solvent. That's the minivan. And the solute is going to try and break up and go find space in there. And that takes energy, all right? So there's a balance between the attraction from here to there and the amount of energy required to make room. It's kind of weird, but it makes sense. You see it like on a church bench too, where everyone, like, here's all your rows, and the late family that comes every time, they follow in, and the stupid dad wants to be in the end. So he sits like right here. And you're like, okay, dad, you can sit there and flex, but you should be at the end of the people going in, not the first. Because then the dad's got to like scoot back and look like all crookedy and then gets a cramp. And you know what I'm talking about. You know what I'm talking about, because I just cramped myself and I'm a dad. All right, there's got to be room. But look, now that there is room and it moves in, now there's an interaction that could be a positive or negative, like increase or decrease of energy between the new attractions. So there are 3 things that you got to think about: the attraction of the solute to the solvent, how hard it is for it to make room for the solute, and then the exchange of energy after they form their new attraction between the solute and solvent. It's kind of tricky. Okay, so I have a video to show you. Maybe I already have. Have I ever showed you the really hot ball in water?
Yes.
No, you didn't. You showed us.
No.
You showed us in real life too.
I showed you. Oh, it didn't work in real life very well.
I'm
No, I'm just great here. Okay, so we already kind of talked about that then. These three steps, when they combine, will either give you enthalpy change where heat's given off, which we call exothermic, or heat's taken in, which is endothermic. Are you all right with that? What? I still didn't hear you because she coughed at the wrong time. Oh, it did. Okay, thank you, Abby. You're trying. All right. So the enthalpy change of the overall process depends on the delta H for each of these processes. You okay with that? Okay. Now I skipped a bunch of slides. We're going to talk about them now. It's important that we review what an endothermic and an exothermic process does. You with me? Yep, there you go. If the ball is hot, we define the ball as the system. Do you remember this? And the everything else are the surroundings. You with me so far?
Yes.
Okay. If I put a hot ball, let me make that red. That's just disconcerting. It can't be black. If I put a hot ball in water, where's the heat going to go? All right. So this would be like an exothermic process, right?
Yes.
Because the system lost heat, or to help you with vocabulary, the heat exited the ball. You okay with that? The system lost heat / energy. You with me? All right. Now, that means the surroundings did what? Gained heat. It got hotter. So if I were to take my completely skin-colored hand and don't even worry about it, and I were to touch this, what would I sense? Heat. Because your X is really hot. And now we remember good. Your X, you dumped him, he was hot or she was hot, well, they were really negative. Whatever. We okay with this so far? Why is it negative? This is the part that tricks people up, remember, please. Okay, because the energy left the system. So the E initial would be when the ball is hot, right? So let's say it's 100. E final would be when the ball has cooled. So whatever number, I don't care, 50. So my delta E, final minus initial, gives me a negative number. So exothermic things are negative, and we sense them as giving off heat, or they're hot. Okay, which we had, our X was hot, but they were too negative. Okay, now that's putting a hot ball in water. Can anyone get super deep and creative and think about how we could do this for an endothermic process? What would we put in water? No. Put a piece of ice. Yours was right. Yours was right, but like we do this one all the time. All right.
Okay, scientifically, we should prove that water tastes better cold.
It's not hard, but I won't teach you. I assume Blaine knows. All right. Endo, please listen. Endo we feel as cold because the heat leaves the surroundings and goes into the ice to melt it, right? If heat leaves the surroundings, and my completely realistic looking hand, I'll do better this time. broken wrist. All right. Don't even worry about it. Okay. I would feel this is cold. But why is it positive?
It's getting hotter.
Because energy entered the system. You okay with that?
Initial is what?
Okay, this is a review, and I think we're basically out of time. We have a minute and a half. But we're going to talk about endo and exothermic processes tomorrow, which we already have, but with respect to solutions. Okay, we're probably going to test in 2 days.